Balancing redox reactions is not as simple as balancing regular old reactions. Oftentimes in redox reactions, we have, spectator ions that we don't include. We have complex electron transfer processes that are happening that sometimes require the presence of either acid or base. In this video, we're going to learn how to balance them in acidic conditions, which is how we're going to be doing it for basic conditions as well, though basic will have a few more steps at the end. Sorry, my head is in the way. When we're balancing a redox reaction, we have to identify what are called the half reactions. So our first step is identify what are called half reactions. And here we're looking at what is happening with the oxidation and reduction here. We want to get rid of all of the things that don't have anything to do with our reaction. So we're going to eliminate any spectators that may be present. And we're going to write our equations as what are called half reactions. So one for oxidation, one for reduction. Looking at this, we can see that we have sodium, which as we remember, is always a spectator ion. So we can get rid of it. Let's get rid of that pesky sodium. By doing so, we'll be left with this bismuth polyatomic ion. The sodium would have provided a +1 charge to balance that out. So we can hopefully see our half reactions here as ones where we're looking not at oxygen and hydrogen, but at everything else. So we can identify one half reaction will be this manganese turning into permanganate. We want to keep, we don't care about hydrogen and oxygen and all that. We only care about the things that are being oxidized and reduced. And generally those are easy to see, just like you could identify acid-base pairs. Or like, what's the acid, what's the base in a reaction? If you've got manganese on one side and manganese on the other and it's not a spectator, then that's going to be one of your half reactions. In this case, the other one is going to be the bismuth one. So we have this bismuth polyatomic ion turning into bismuth 3+. Those are your half reactions. And we're going to balance them each the same way. So we're going to follow the following steps. The first thing we want to do, which I guess is now step 2, after we've identified our half reactions, is we want to balance all non-hydrogen or oxygen elements. So if we look at we can do both of these simultaneously. If we look at our manganese one, we have one manganese on each side. Don't care about oxygen yet. For the bismuth one, it looks like we have one bismuth on each side. Don't care about the oxygens. So that's great. Check. Done. Nothing's changed. Next, we want to balance oxygen by adding water. And so we're going to be adding waters to the side that doesn't have the oxygen or doesn't have enough oxygen. So for example, in our first equation there, we have oxygens on the right, no oxygens on the left. So we're going to add some waters. Since we have 4 oxygens on the right, none on the left, we're going to add 4 waters here. So adding 4 waters will bring our oxygen into balance. And we can do so for the following reaction. We can add 3 waters to our bismuth one because we only have 3 oxygens there that are missing. So, ta-da, we have done step 3. Step 4 is now to balance. Balance. One day I will spell balance correctly on the first try. We're going to balance hydrogen by adding H+. So we can go ahead and do that. If we look at our first reaction, we have 8 hydrogens on the left, and we have 0 on the right. So we're going to add 8 hydrogens, ions, H+. Hydrogen ions are being added. And on the left side, it looks like we're missing 6, so let's add 6 hydrogens. And then the last thing we want to do is balance the charge. by adding electrons. So, if we look at our first reaction, on our left side we have a +2 charge, and that's it. Overall, we're looking at +2. On the right side, we have 8 positives, 1 negative, that's +7. So if we have +2 on one side, +7 on the other, we're going to want to add, in light blue, we're going to add 5 electrons, because electrons will give negative charges, right? So to bring the charge into balance, we're going to add electrons. So we had +7 on the right, +2 on the left. To balance that, we have to add 5 electrons to the right side to counteract that extra positive charge. And lo and behold, with this one as well, we have +5 on the left, +3 on the right. Therefore, we're going to need 2 electrons on the left to balance this out. And we will have our half reactions. Something to notice that all of these have added to the opposite sides. That's a good thing. We want to see that, especially the electrons. Well, technically, yes, sometimes we will have to add water both to the products in each reaction. Since these are half reactions, one representing oxidation, the other representing reduction, we're going to want to make sure that we have our electrons on opposite sides. It will not make sense if we have them all, on both reactions, the electrons are in the products or something. Doesn't make sense that way. One of them should be products, one should be reactants, especially for electrons. And now, the last thing that we do is we're going to add these up. So we are going to add the equations together. But first, multiply as necessary to get the electrons to cancel out. So if we take a look at our first reaction, we have 5 electrons. In our second reaction, we have 2 electrons. If we need those electrons to cancel out, we can't just add them directly. We're going to have to multiply both of these together. So we're going to need 2 of this one so that we have 10 electrons total. And we're going to need 5 of the bottom one. Right? Does that make sense? So that you have 10 electrons now in both reactions. Now we can add them together. The only things we really need to make sure cancel are the electrons. Everything else can be whatever. We will subtract later once we do all the math. So, not math, adding and subtracting. I guess that is math. Okay. So, let's go ahead and now list everything in our reactants. We have 8 waters, plus 2 manganese 2+ ions, plus 10 electrons, plus 30 hydrogens, plus 5 bismuth ion thingies. Don't know the name of that polyatomic ion. We now have 2 permanganates. I'm writing our products down here because these are often very long reactions, so often we'll need 2 spaces. We have 16 hydrogens, and we have 10 electrons, and 5 bismuth ions, and 15 waters. And so now we just need to get rid of things that are the same on both sides. For example, those pesky electrons that we don't want to see present in our final balanced reaction. We note we have 30 hydrogens on the reactant side, 16 on the right. If we get rid of 14 of those, we can do that. Looks like we have 8 waters on the left, or sorry, reactant side, 15 on the right. We can get rid of 8 of those. So now we're going to have 7 waters. And nothing else can cancel out. So now we can finally rewrite this and be done with this lovely problem. We can have finally 2 manganese plus 14 hydrogens plus 5 of this bismuth thing goes to 2 permanganate plus 5 bismuth 3 ions plus 7 waters. And so that is our overall reaction. And you see how difficult these are to balance? They're not difficult, they're just a lot of steps. So in our next video, we're going to do the same thing, but in basic conditions. And as we will see, basic conditions will be the same as acidic conditions, except for one last step that we're going to do. And so we'll do that in the next video, so you can see another practice problem for balancing these equations as well.